In this module, we are going to see how we can represent an ideal refrigeration cycle on a pH diagram. Now first, note that for any chemical substance, and we are of course looking at refrigerants, that there is a very defined relationship between temperature and pressure. So if you look at the pH diagram, on the left hand side we have the pressure expressed in bar, and if you follow the horizontal line, you will see that where it crosses the saturated liquid line, there is a temperature, and if you continue on to the right hand side on the same horizontal line, you will see the same temperature on the saturated vapor curve. So we note that there is a distinct relationship between the temperatures and pressure. Now in any refrigeration system, there are always two pressures. One is the low pressure and the other is a high pressure. If you happen to go to a refrigerated warehouse and you walk over to the room where they have all the compressors and all the equipment that is being used to run the refrigeration system, you will always notice two pressure gauges. One of the pressure gauges will tell you the low pressure in the system and the other one the high pressure. Now from the previous modules you will note that the low pressure side is for the evaporator and the high pressure side is for the condenser. So on this pH diagram again we notice that there is a low pressure and a high pressure, and correspondingly there is also a temperature. For low pressure we have the evaporator temperature, and for the high pressure the condenser temperature. So in a problem that you might encounter, you will be always either given the two pressures, the low pressure and high pressure, or you will be given the two temperatures, the evaporator temperature and the condenser temperature. So with those two values, either of pressures or temperatures, we can proceed to draw the ideal refrigeration cycle. Note that for most calculations involving the design or evaluation of a refrigeration system, our goal is to find the three enthalpy values H1, H2, and H3. I'm going to enlarge the view for a part of this chart to see a little more clearly what we have. And it will be good if you have a copy of a chart separately that you can look at and follow along as we draw the refrigeration cycle. So we will use the low pressure or the evaporator temperature to draw a horizontal line. So as we see on this chart, the evaporator temperature was given as 10 degrees C, and therefore we have drawn a horizontal line that connects the 10 degrees C both on the left hand side and the right hand side under this bell-shaped curve, and we have the lower part of the cycle. Similarly, we will use the high pressure value or the condenser temperature to draw again a horizontal line connecting either the two temperatures. So in this example we have 40 degrees Celsius as the condenser temperature, and we have drawn a horizontal line on the top. Now from the point where the lower horizontal line, which was for the evaporator, where that meets the saturated vapor curve on the right hand side, we will draw a line that follows the constant entropy curve. So we need to follow a constant entropy curve. Remember that the constant entropy curves are plotted on the chart, so you need to follow one of those curves so it slopes outward, and you extend that curve all the way to the top where it meets the constant temperature line for the condenser. Now note that it can be sometimes difficult to exactly follow a constant entropy curve, but do the best that you can, either to visually interpolate between the neighboring constant entropy lines, or if the originating point happens to coincide with where the constant entropy line originates from the saturated vapor curve, you can essentially follow that line. So note that the constant entropy curve inclines outward away from the saturated vapor curve. On the left-hand side, where the top line for the condenser meets the saturated liquid curve, so drop the vertical line all the way to the constant evaporator temperature. So this gives us our ideal refrigeration cycle. Note that we can now write the letters E, A, B, C, D, which, if you recall, refer to the locations on the schematic of a refrigeration system, as we had seen in a previous module. Note that for E to A, we have the evaporator section, A to B is the compressor, B to C is where the superheat is removed. Note that point B is in the superheated region, so to go from B to C, you first discharge the superheat, and then from C to D is all the heat that is discharged in the condenser. And quite often the heat discharged for the condenser is considered to be from B to D. Now from point D we have a drop in pressure all the way to point E, which represents the expansion valve. Note that D to E is an adiabatic process. Recall from your chemistry, adiabatic means the enthalpy remains constant, and that's why it's a vertical line. The enthalpy at point D and point E is the same. So the expansion process is always an adiabatic process. Now we can view a short animation where it shows again that we have the two horizontal lines, and for the low pressure and high pressure, and then we complete the cycle by following the constant entropy curve on the right hand side and a vertical line that drops on the left hand side from the point where the condenser line meets the saturated liquid curve. So I hope this has given you a introduction to how an ideal cycle is drawn on a pH diagram, on a pressure enthalpy diagram. And in some of the following modules we will work with some examples to see how we can get numerical information. That involves both superheating of vapors exiting the evaporator and subcooling of the refrigerant leaving the condenser. So let's consider an example. We have an evaporator running at a temperature of 0 Celsius, a condenser operating at 40 degrees C, and the vapors exiting the evaporator are superheated by an additional 10 degrees C, whereas the refrigerant leaving the condenser is subcooled by an additional 10 degrees C. So let's see how we can represent this on a pH diagram. First thing we will need to do is draw a line for the evaporator temperature, which is 0 C, starting with 0 degrees C, which is shown on the saturated liquid curve. We draw a horizontal line until it meets the saturated vapor curve. However, we will need to extend this line further into the superheated region because the vapors leaving the evaporator are superheated by an additional 10 degrees C. So what we need to do is extend this line until it meets the 10 degrees C constant temperature curve. Remember that the evaporator temperature is 0 C, so if we add the additional 10 degrees C because of superheating, the temperature of the vapors will be 0 plus 10 or 10 degrees C. So the line must be extended to meet the 10 degrees C constant temperature curve. So this is the point where we will need to follow the constant entropy curve. But before we do that, let's also draw the horizontal line representing the condenser, which is operating at 40 degrees C. So we identify 40 degrees C under the saturated liquid curve, and the same temperature, of course, we see on the saturated vapor curve. So we draw the horizontal line and also extend it into the superheated region. Next, we start from the point that now represents the superheated vapors leaving the evaporator, and we follow the constant entropy curve all the way to the point where it meets the line for the condenser, and we identify that point on the top right hand side. So that will be the location that will represent the exit of that superheated vapors from the compressor. Now on the left hand side, note that the condenser is operating at 40 degrees C, but the refrigerant leaving the condenser is subcooled by an additional 10 degrees C. So 40 minus 10 will be 30 degrees C. That will be the discharge temperature of the refrigerant from the condenser. So we will identify where we have 30 degrees C shown under the saturated liquid curve. And so from that point, we will draw a vertical line which will represent a constant temperature line for 30 degrees C to where it meets the line for the condenser. And we will also extend it all the way to where it meets the evaporator line. Note that the point in the subcooled region now is identified, and the temperature of the refrigerant leaving the condenser in the subcooled state is at 30 degrees C. So here we have this cycle representing both superheating and subcooling, and we will clean up the any of the extraneous lines. And we will also identify the points E dash, A dash, B dash, C dash, and D dash, representing the superheated and subcooled state shown on this chart. And let's also look at an animation that shows how a cycle representing both superheating and subcooling can be shown on a pH diagram.